In the last video, we looked at how to classify stationary points. So if we have f dash of x is equal to 0 and f double dash of x greater than 0, we have a minimum. If we have f dash of x equal to 0 but f double dash of x is less than 0, we have a maximum, and I'll explain why this is true in the last video. So there's clearly one other case here, and that's when f double dash of x is equal to 0. So what does this imply? Well, really it tells us nothing. The truth is we could have a max, a min, or something called a point of inflection. And a point of inflection is essentially, if you have a graph, a minimum, a local min when it turns, local max when it turns again. But a point of inflection, a point of inflection in general is when something changes concavity, I don't know how to say that word. Anyway, essentially when the rate of the gradient changes. But in this specific case, when we're looking at stationary points, it's when the rate of change of the gradient changes sign, but also we have a gradient of 0. So in general, that might be a point of inflection, but not as far as we're concerned, because this doesn't ever have a gradient of 0. You see, the gradient's increasing and it's increasing, but that's not what we're looking for. We want something similar to that. What we want is something 0 like this, but then instead of going back down, it goes back up again. Alright, sorry for that terrible drawing. See, what we've seen so far is that when they start to decrease, they just keep going. But a point of inflection, as I say, when we're looking at stationary points, is one that goes up like this, in and then back out. It could also be going down and do a similar thing. What we'll do is, we'll do an example and where the second derivative is equal to 0, and then we'll use, because this, if the second derivative is equal to 0, this technique has failed in telling us what we want to know about the stationary point, so we have to investigate in a different way. So we'll get onto that now. So we're looking at this function, y equals 12, x plus 1 cubed plus 6. We'll take the first derivative to find the stationary point. We're going to use the chain rule here, so we treat this x plus 1 as u, so we've got u cubed and 12u cubed, so that goes to 36, and then 36u cubed and u's x plus 1, sorry, u squared, and in the chain rule we do have to multiply by the derivative of this u, but the derivative of x plus 1 is just 1, so that's fine. This plus 6 just disappears, so if we set this equal to 0, this gives us the solution. Well, 36 isn't equal to 0, so x plus 1 is to be equal to 0, and that means the only solution is x equals minus 1, the only real solution anyway. So we want to try classify the stationary point, so we go to our number 1 technique, which is to find the second derivative, and this is equal to 72 x plus 1. Now we substitute minus 1 in, so 72 minus 1 plus 1, well, that's equal to 0. So we haven't gained any information about the stationary point here. We just know nothing. So what we're going to do is, we're going to find the y coordinate of this stationary point, So substituting -1 and putting that in there just gives us y equals 6. So our stationary point is at -1, 6. And now we're going to look at x coordinates just either side of it. So when we're going to put x equal to -2, that gives us y is equal to 12 -2 plus 1 cubed, and that comes out equal to -6. And then at x equal to 0, we get y is equal to 12 0 plus 1 cubed plus 6, and that's equal to 18. Right, but at -1, y is equal to 6. So at the point just below, the y coordinate is smaller than our stationary point, and at the point just past it, the y coordinate is greater than. So we know it's not a min or a max, because if it was a max, both of these would have to be lower than 6, and if it was a minimum, both of these would have to be greater than 6. So we know we've got that this point is a point of inflection. And a couple of side notes: you could use this technique to investigate all stationary points. Really, you don't have to look at the second derivative, but that's just, the second derivative is just convenient, and when it's positive and negative, which it is most of the time, it just pops the answer right out, which is very helpful. Also make sure you select close y values. If I select -10 and 100, well, that's not helping me, because we're looking for local maxima and minima. You can't just, so you have to look at things close by to -1. Maybe even if you're using a calculator, you might want to look at -1.5 and -0.5, just to get sure you're right and tight around the point, and you're just trying to see what happens just around that section. But yeah, other than that, that's it for this video. I think from the next video we'll possibly get onto integration. We're done with our differentiation for now. If you did enjoy the video, please like and subscribe. If there's something else you want to see, then be sure to comment that below. But for now, I hope to see you in the next one.